All right, so hello, my name is Kevin McLLVain. I'm a memory development engineer with IBM. So before we get started, I just wanted to quickly touch on, I'm on. I come from a hardware background, right? So I've done hardware for quite a long time. I've been really involved with our previous memory buffered solutions for P8. Did a lot of the design for both the memory controller and test engines on that chip. Was involved a lot in the bring up with that. Now I've been involved with the direct attach memory subsystem bring up for our P9 systems like the AC920. So what I want to touch on now is the OpenCAPI memory interface and why it's so important, why I'm excited about it, why I hope everybody else will be excited about it too. So I just want to cut to the chase here too, is like what is the moral of the story here, right? So you're not waiting until the end to figure it out, right? So the moral of the story here is that the OpenPOWER is the best platform to exploit emerging memory technologies, right? We've already seen that in a lot of the presentations earlier in terms of like all the accelerator work that's been going on with the OpenCAPI interfaces and things like that. But there's more to come, right? With the next generation of P9 that's going to be coming out with the OpenCAPI memory interface. We've touched on that in some of the other conversations, the OpenCAPI 3.1. We just know that it's a forward-thinking architecture. We're going to be, we're accepting the technology scaling challenges, and the OpenPOWER is architected to solve those issues, right? So it's not just for GPUs and other accelerators. Now it's for memory too. We have to really start thinking about the changes in the upcoming memory subsystem. So OpenPOWER recognizes that memory is at the forefront of transforming system architecture, right? So namely, we're looking at the memory agnostic interfaces so we can attach all types of different memories. The OpenCAPI 3.0, the 3.1, and the upcoming 3.1 and 4.0, right? We're no longer going to be tied to a specific media like a DDR4, right? So that makes it much easier to manage your technology transitions from DDR4 to DDR5, emerging memory technologies, things like that. And we've learned a lot of that in the past with our other buffered memory solutions, transitioning from DDR3 to DDR4. So there's also going to be firmware support for new memory technologies, for persistent memory. We're already working on, in the OpenPOWER, right, is to provide a mechanism in firmware to support persistent memory, right? So when we start attaching these persistent memories in, the system can utilize those, right? And we need this open ecosystem for fast industry research, development, and adoption, right? We're at the precipice of big changes in the memory subsystem, and OpenPOWER is ready to lead the way. So we've looked at a lot of graphs earlier today in other presentations about the scaling challenges, right? One of the things that we don't talk about so much anymore is the old von Neumann's bottleneck, right? So your throughput's always limited by what your memory bandwidth capabilities are, right? And in the past, there's been a lot of processor technology that's evolved to help alleviate those throughput issues, some of those being caching, prefetch, and multi-threading. And then also it's like, it's holding hands with the Moore's law, right? So the shrinking devices and increasing speed, right? That's caused a lot of changes in the compute architecture to compensate for the now slowing Moore's law, right? So you're increasing your core counts. So what we have to do, you're starting to augment your processors with GPUs and FPGAs, specialized accelerators, which are all connected now with advanced IOs, right? So this is requiring more memory and memory bandwidth and density, right? So, but we can't just think about what's happening to the processors and trying to scale the processors. We have to also think about the memory, but the memory is starting to hit a lot of limitations too, right? So as we start to move forward from DDR4 and we're looking at DDR5 coming up, we have on-chip ECC, right? Because as the devices are shrinking, they're not holding as much charge anymore. So every time you do a read operation, that device is checking and doing an ECC check and might do a read modify write. So that's going to add latency to your devices. And then also the interface out to your DDR memories, right? So it's got to employ things like DFE, right? Because we're starting to reach the limitations of the single-ended memory interface, right? So with that, it's adding cost, it's adding latency. We're starting to also see power, density, and scaling limitations. So these are some charts that were shown in the JEDEC server forum. Credit to KH Kim, but What it kind of shows here is the power processor trend over on the left, right? The main message there is as you add more cores and more threads to equal more higher performance per socket, your memory capacity also has to increase to match that, right? So each one of those new cores and threads is going to need more memory bandwidth going to it, right? And then here on the right is the problem that we've seen, listed in some other presentations like Ken's earlier, is that your DRAM die density is starting to flatten out, right? And you're starting to increase your cost, and you're not getting as much benefit out of that from your DRAM devices. So what does this mean, right? What are the challenges? So if we look over here on the left, right, this is a typical pyramid. We've seen them a lot. It's around the industry quite a bit in a lot of presentations. But it basically shows your memory stack and how your decreasing cost is applied as you move out away from your processor. And then also the access times to get to those devices. So what's happening, right, is all these AI type applications, for instance, right, as an example, require a tremendous amount of memory bandwidths, and it's driving a massive increase in memory capacity. So your DRAM technology is beginning to face the scaling challenges like we mentioned before, but you still require low latency DRAM devices to be attached into your system, right? So that requires you still have to grow your capacity and bandwidth though, right? But your costs are also becoming a major inhibitor. So what you have to start doing is we have to start now augmenting your DRAM devices, much like we've been starting to augment all of our processors, right, with GPUs and things like that. So now we have to augment the DRAM with emerging memory technology, right? You're still going to require different tiers for DRAM for low latency. So the idea here is to significantly reduce the cost of your high capacity memory, right? So heterogeneous memory architectures are the next logical step, right? So how do we get there? What's the best path forward? So in your traditional memory architectures, right, you would have your memory directly attached to your CPU through the memory controller. Then you have flexible I/O, OpenCAPI, PCIe, talking to a storage adapter. It's just a basic example, right? But where can we add the most value? So everybody's been looking at trying to move storage class type memories up to your direct attached memory locations, right? So we're talking about hybrid DIMMs like NVDIMM, F, P, even H. H is, that's proprietary from some other companies. But the main one here is the P, right? That's the one where you actually really get to start utilizing the storage class memory that's out there on the DIMM. It's not just there to be like a backup, right? In the case of an NVDIMM. So as you start to move all those bits out there, right, you need more bits, more bandwidth, right? But what are the challenges with doing that, right? You're still tied to a DDR4, DDR5 interface. And your protocols are specific and not very flexible, right? So it's difficult, again, to manage your technology transitions. And in specific with the NVDIMM, when you go out into the industry, like when you're talking in JEDEC and you're working with some of the memory vendors, they're very concerned about what's going to happen there. What is the support going to be for the NVDIMM protocol, right? There's a lot of work going on in the work group, and they're coming out with the spec. But what they see is that the biggest processor, guy out there is coming up with his own solution, right? And that's going to be a proprietary extension on DDR4, right? So there's this 3D cross point, right? So it's a proprietary extension on DDR4 for only a single SCM technology. So what we see is that restricts innovation and cost per gigabyte competition, right? So it also compromises bandwidth and capacity with your DRAM tiers and your versus SCM tiers, right? So there's some other, just the architecture and the way that it's currently slated to work in the system, right? Because you're taking away a memory channel to put this on. So there's a lot of concern, right? So if other memory vendors go out and they try to make their own devices and attach to NVDIMM, where's the volume going to be for them, right? How are they going to innovate? How are they going to apply into the architecture, right? So we can add a lot of value through the OpenCAPI memory interface, right? So by making this interface agnostic, right, we're able to embrace all the diverse memory technologies that are coming. We encourage innovation in the industry, right? But it's not just limited to the OpenPOWER CPUs. I mean, right now, obviously, with OpenCAPI, the Power architecture is the only place where it's being used, but that doesn't mean it's the only place it's going to survive, right? We've already heard talk from other companies, with concerns about the scalability of the DRAM direct attach interface, and showing more and more eyes opening up to what we're doing with the OpenCAPI, saying, hey, this really does look like a great solution moving forward. Right, so some of the other things that are great about this is you get the more bandwidths and the more bits, right? So you have fewer pins than what you would see with the normal DDR4, DDR5 interface. So in comparison to DDR4, the OpenCAPI is about 34 pins versus 150 for one memory channel. So that's like a 4.4x reduction in pins, right? So 8 channels of DDR4 on the P9 is about 1,200 pins. That's huge. And then your OMI is 2x the bandwidth for half the pins. So that's a pretty huge reduction, right? So that allows you to do a lot more differentiation on your processor in addition to adding a lot more bandwidth, right? Because you can use that other pin space for other feature. So a couple other notes, and we'll talk more about this on a table later, is that your DDR4 and OMI, if you look at channel per channel, have equal max only read bandwidth capabilities. And the write is the same way. But the OMI can support that same read bandwidth and write bandwidth at the same time, right? So it's almost like getting 2 DDR4 channels for one. So there's also, this gives you the capability to support, possibly up to 16 OMI channels per processor. This is perfect for emerging heterogeneous technologies and your memory acceleration. And it can help you optimize your memory tier bandwidth and capacity for lower total cost of ownership, right? Also, there's the drive to push this through JEDEC. We're working through JEDEC and different task groups to create a standardization for the DDR5 DDIMM, right, which will have an OpenCAPI interface. So this is a quote from somebody sitting in the room. So Jeff. So I just really like this quote, right? This came out of the Hot Chips article, right? So this really talks about the flexibility of the attach, right? And just being able to drive a ton of bandwidth through the CPU. It's the big switch, right? You got to pass through all your memory bandwidth from one capability to another. It really helps you tie in everything in your system. And one of those things is going to be your memory, right? And depending on what kind of GPUs and everything you have out there, they may want to utilize the memory subsystem differently, right? So depending on what you have out there in terms of emerging memory or direct attach DRAMs, you can really optimize your total solution together. So this is kind of the chart of, where we've been in the past, right? So this is your Power 8 architecture. So even back then we had the DMI interface, right? And this is kind of where the OpenPOWER memory Workgroup started, right? With this differential memory interface. It was an agnostic interface, which was great. You could attach whatever you wanted out there. We've done research on that interface. We've put FPGAs on there with emerging memory. We've done all that kind of stuff, right? And we learned a lot, but we also know that, hey, we learned that this is proprietary. Nobody likes proprietary. When you're trying to work through an open architectured system and you want to drive innovation, you have to open everything up, right? So, but it was, initially it was used for other reasons, right? It gave us the high bandwidth, the big densities. And when that was initially architected, it was still at that rise up where you could keep scaling your DRAM technology. It wasn't quite leveling off like it is now. So then we kind of realized that we needed low-end solutions where we had direct attach, right? Because that allows people to take something that's not a customized DIMM and plug it into a system, right? That allowed you to go out into data centers and put in your P9 systems, and people could bring over their own DIMMs, things like that, right? So at the OpenCAPI memory interface, we're trying to do the best of both worlds, right? We're trying to have this agnostic interface with super high bandwidth that really supports emerging memories, but we're also trying to do the standardization through JEDEC so that we can move forward and try to get more people to adopt it, bring up that ecosystem with the different memory vendors that are out there to try to drive down the total cost of the DIMMs, right? That's not going to happen initially, but it's it's a progression, right? You got to start somewhere. So we're starting with that, with the JEDEC strategies. So if we move forward and we talk about, what are we doing in the OpenPOWER memory Workgroup with the strategy going forward, what do we need to start talking about, right? We need to start working with the new interfaces that are coming down the path, right? We think that this OpenCAPI 3.1 memory interface is really something substantial to work with. We already have a lot of work going on with the OpenCAPI 3.0 and the LPC modes that we've talked about in some of the other groups, especially some of the heterogeneous and hybrid memory work that Ken talked about earlier. And we need to also support a roadmap for these standardized DIMMs. So that's building another ecosystem too, right, through the OpenPOWER ecosystem to enable all of your memory vendors to go off and build these new DIMMs, right? Because it's a huge undertaking for them, right? They see, you know, they know how to test industry standard DIMMs. That's what they like. They can touch their own memories through the interface. They can wiggle the bits on those. Now they have to talk through a buffer chip, right? But we've been through that in the past with the buffer DIMM solutions for the P8s, right? We know how to work with them on that. We know what their concerns are. So we're also working with them to figure out all the best test solutions to build into buffer chips that should be standardized in the buffer chips to try to build up this ecosystem to drive the cost down on these DIMMs, right? So it's not just thinking about innovation as really working on the accelerator part and all the, you know, speeding up and blending all the heterogeneous stuff together. That's a huge component on where we need to move forward. But there's also the now part of it, right? We need to start making DIMMs now to support the next generation of systems where we're replacing direct attached memory, right? So at that standpoint, we need to start building up that ecosystem through OpenPOWER as well, so that anybody can go off and start building DIMMs if they want to, right? That's the way to really drive an ecosystem. So we're working hard at that as well. So what that includes is building up reference designs. I'll show you one in a few minutes here. Characterization and qualification code for the system developers that are going to build something with these DIMMs, and how do they qualify their memory subsystems, things like that. And then also the verification IP. What if somebody wants to go and build their own buffer chip to put on these DIMMs, right? We want to make sure that they have IP that's available to them, that they can go and drive their emulation environments and simulation environments and things like that. So the goal here is we have to support not just, you know, the research part of it and what we're doing in the work group right now, but I think that the work group needs to expand and bring in the concerns of more people in the area for, you know, the research side of it, and then also just driving lower cost DIMM solutions as well. So here's just a quick chart we've talked about in the work group a bit. This gives you kind of a picture of your bandwidth, right? So across different, you know, some different comparisons. So this is, you know, just theoretical maximums for sustained bandwidth, right? Just for discussion purpose. So if you think of a DDR4 3200 DIMM, this is your near term, right? So that's, you know, kind of industry standard now. One channel, 64 bits per channel, or yeah, 64 bits per channel. Compare that to your OpenCAPI by 8. You get the by 8 read, the by 8 write. So you're at 204 bandwidth for read, 204 for write. So if you do a comparison between your max DDR read bandwidth to the OpenCAPI, right? So you can actually run, you can get 100% read bandwidth, and you're not even really using any of the write side on the OpenCAPI. So think of all the stuff that, the other items that you could be doing. You could send down a lot of stuff there for your emerging memory technology. You can really start to blend stuff with the capabilities that are out there. DDR5, right, which isn't too far off, the DDR5 DIMM is actually, you know, it's like cutting a DDR4 DIMM in half, and you have two 32-bit channels there, right? So you get a little more flexibility in driving bandwidth, write bandwidth, and read bandwidth at the same time, but it's still, you know, so you can do two things at once, right? Or you have the same kind of overall bandwidth calculations for total read, total write, but allows you a little more flexibility in your solutions as well. And then when you get down the road, really far down the road, I don't even know, you know, you always say this is what DDR5 is maxed out for, 6400, but are we ever going to get there? Who knows? But what it shows here is, you know, just some other calculations moving on. But by the time you get here, this would be further down the road where your OMI interface, your OpenCAPI memory interface will probably be much faster than 25. It'll probably be 32 to 50 at that point. So I'm going to skip ahead a little bit because I'm probably getting short on time. So what we want to do in the memory work group right now, right? And there's been a lot of conversations on how we blend this with what OpenCAPI is doing, what the accelerator work groups are doing and all that. And I think we need to have more facilitation on those discussions and just really figure out how we want to move forward and what the right direction is. But we need to have we need to have some sort of hardware support, right? We need to have, hit the wrong button here. We need to have the reference designs to support the OpenCAPI 3.0 and 3.1, verification IP, OpenPOWER partners that can provide OpenPOWER ready hardware. We've already seen a lot of stuff being developed, right? Software support, right? I'm a hardware guy. I want to get more people involved on the software side of things, right? I've seen a lot of great presentations earlier. I think we could probably bring in a lot of what's been done with the OpenCAPI Snap, bring it in here for developing these and applying it to developing the new heterogeneous memory solutions for, plugging into where direct attach would be. So this is kind of a quick overview of what we've been working on in the task group, is developing what this interface is here, right? So the idea is to have kind of hide this whole OpenCAPI stack from the developer on the FPGA, right? So they can develop their own abstracted, their own memory functional unit that hides out here and would just talk AXI, right? So AXI is very, when you're working with FPGAs, it's pretty industry standard. It's out there for, this is, most of the work obviously has been done with the Xilinx stuff, but the AXI is known, right? So to abstract out what you have to do here, it makes things a whole lot easier. So we're specifying how this would work, right, in an OpenPOWER system, not just with OpenCAPI. So in an OpenPOWER system, there's a couple nuances, right? Because if you take the OpenCAPI interface and you plug it into another system, they might use metabits and things like that in a different way, right? So we have to spec out, there'll be a bus that comes across here. It's going to present a command, and it'll have metabits, right? You have to know how to handle those metabits. Anything, particular to the OpenPOWER, right? So that's what we want to focus in the OpenPOWER work group, is how does it work with the OpenPOWER machines. This kind of shows the abstracted view of what would be on the verification IP. So this is actually already in place and being used for the development of the next generation memory buffer, and it's driving the emulation patterns. So we have test engines in there. Obviously, not everything's listed here, but there's a lot of great stuff here that emulates the traffic that would normally come from the host. So you can do very precise emulation and simulation. And then what we can do is you can take that same image and plug it into the FPGA on a test platform that you would give to a vendor, right? So this test platform is also in development, right? And we'd like to make this a reference design that's provided out as needed. But this would go to memory vendors. They can plug in that same verification IP. They can drive the OpenCAPI channels on the board. This happens to be a VU9P on there. So it's set up to drive 4 OpenCAPI channels. We have 2 slim SASs over there to do other work. But this is a general concept, right? So this would have a BMC on it that can run our OpenPOWER toolkit, all the Cronus stuff. There's a lot of great things going on here, but it'd be great to be able to do something here with Snap as well. So we can talk a lot more with anybody offline about this after this discussion. But next, as I mentioned before, we need to get more software support, right? We want to get more support for different types of characterization, qualification code, right? There'll be a lot in there that's available for testing the standardized differential DIMMs, but as people start to build interesting, different types of heterogeneous memory that's going to plug into a DDIMM interface, we imagine that there'll be other IP, right, that would go out onto the FPGA they could use to drive the workload to test specific devices. So it's a very flexible platform, right? Let's see here, what else? So we just need to do that, bring more discussion to the work group, and really figure out how we want to move forward. So that's really what I want to talk about with facilitating the IP. This is just a chart about what the overall listed description and scope of the current work group is. And I think we need to decide if this really applies and how we want to move forward with both the OpenPOWER memory work group. Do we need one in OpenCAPI? How do we make this all work together? So that's it. So thank you.